Hello, Earth Science students. This is Dr. B. We're doing High Adventure Science. Will there be enough fresh water? Activity 6, and we're just beginning. We're going to understand how to use groundwater wisely. We're going to use interactive computational models to investigate the relationship between infiltration, that's water getting into the groundwater, and recharge in natural and urbanized areas. Explore how human development has changed the natural flow of water. Explore the transfer of water from one aquifer to another, and propose solutions to allow for water extracted from wells to recharge the aquifers from which they came. So let's start with page 1, recharge rates. The placement of pumps can affect the water level in streams, rivers, lakes, and ponds. We found that out in activity 5. The amount of water that is pumped can also affect the surface bodies of water. As you can see from the diagram, precipitation infiltrates into the ground to replenish groundwater sources, but it takes time for aquifers to be recharged by precipitation. So here's the water cycle. We all understand how rain can infiltrate or slowly seep into the ground and then into the aquifer. But it takes time for that to happen. What type of sediments or rocks will allow the fastest recharge of aquifers? Well, probably sediments with high permeability from what we've learned so far. But let's explain that answer. Well, we know that permeability means how fast water can travel through a material. So if we have high permeability, we're going to get high infiltration rates, which means the rate at which the groundwater is recharged is going to be much faster. How certain are we about our claim here that rocks with high permeability allow faster recharge? And we should think about this in terms of, we have a great model. We also understand permeability and how that works, but we don't have actual data. We don't have data from several different situations in which an aquifer has recharged, and we know what kind of materials are above it. So I'm going to give you some hints for question 4, and you can take those and write your answer. So you can select your own certainty rating, but you can consider, we know high permeability leads to what kind of infiltration rates. We have a model, but we don't have numbers from a real aquifer. It would be best to have data from many aquifers. Let's go to page 2. Runoff or infiltration. The water cycle has been greatly affected by humans, particularly in the amount of water that's able to infiltrate the ground to recharge aquifers. How is infiltration affected? A majority of humans live in urban environments, which are covered by impermeable surfaces, like roads, sidewalks, and roofs. The diagram shows the water cycle in urban areas. So there's much less infiltration in urban areas. For example, here in St. Paul, about 50% of surfaces are impermeable. So that leads to least infiltration. And locally, there are a number of projects to work on, collect stormwater and let it infiltrate to lead to more groundwater recharge. So we need to think about what types of sediment allow water to penetrate. Permeable sediments or impermeable sediments. Permeable means water can pass through. Impermeable means water cannot pass through. What kinds of surfaces make up a large percentage of urban areas? Permeable surfaces or impermeable surfaces? Similar amounts of precipitation fall in urban and non-urban areas. Why is a river in an urban area more likely than a non-urban area to flood during heavy rains and dry up during dry periods? Think about what you've seen when it rains in your city. If you have impermeable surface roads like blacktop, or you have concrete sidewalks, you've probably seen the rain run off these surfaces. And maybe you have storm drains and you've seen a lot of water running to their storm drains. And think about where those storm drains go. Where does that water go when it goes in the storm drain? I gave you a few hints for question 7. Think about impermeable surfaces and precipitation, that's rain or snow or sleet. Where does the water run? And then what happens to the water after it goes in the stormwater system? In Minnesota, we have in Minnesota and many other parts of the country, there's actually programs to adopt a storm drain and sweep it up, rake it up, pick it up, make sure plastic and things like that are not going in your storm drain, and keep all of our rivers cleaner. So think about adopting a storm drain. So let's head on down to question 8, 9, 10, and 11. Are aquifers that lie beneath urban areas recharged by rainfall? That's a good question. Are there some impermeable surfaces? Is it enough to recharge the aquifer? We don't know. How certain are you about your claim based on your explanation? And explain what influenced your certainty rating. Well, I'll give you a few hints here. So I gave you some hints for question 9. There are many impermeable surfaces in cities. Precipitation is often moved off these impermeable surfaces through stormwater management practices like storm drains. And there are some permeable surfaces in every city. We don't know how many permeable and impermeable surfaces there are. And so I'm going to be a little uncertain on this. I explained why I'm a little uncertain. You can choose your own certainty rating here in question 10. I gave you a few hints, like each city has different amounts of permeable and impermeable surfaces. We don't know how permeable the permeable surfaces are, if they infiltrate quickly, if the water moves through that sediment quickly or not. Some cities have built structures that allow stormwater runoff to recharge the groundwater, such as rain gardens and retention ponds. They hold some of that stormwater and let it slowly leak into the ground, so it infiltrates and recharges the groundwater. Now we're on page 3 of activity 6. We're doing rural and urban aquifers. We're using a model that allows us to compare the effects of pumping groundwater from below urban areas and rural areas. The left side of the model shows a rural area. The surface is permeable to water. The right side of the model shows an urban area. The surface layer is impermeable to water, so we see a lot of pavement here that doesn't let water infiltrate. There are 2 types of wells, flowback wells and non-flowback wells. Flowback wells supply water locally for plants and animals. So a well over here on a farm that's pulling up water and putting it on the fields, and then that water can infiltrate back down, is a flowback well. A non-flowback well can be used to pipe water further away from the source. So if we put a well here and piped all that water over to the city, that would be a non-flowback well. This groundwater doesn't get recharged by the water that's pumped from it. Flowback wells can recharge the local aquifer, but water from non-flowback wells is eventually removed from the system. Place 2 flowback wells, one in a rural area and one in an urban area. So let's see what happens. We'll add a well in a rural area here. Put it in the middle of the aquifer. We found out that was a good place. We'll put well number 2 here and just hold our mouse button down to adjust how deep the well is, and then we can hit play. So we can see that it's precipitating. We can see the water piling up here in the city. and it's probably running off somewhere. It might run off to this aquifer a little bit. And we see this aquifer getting pretty low pretty fast. There's still a lot of water in this aquifer. There's a little shape here around the well, but here it looks like it's getting pretty low, and the water up here isn't returning to the aquifer. Let's look at the well output here. Well number 1 looks fairly steady, but well number 2 is declining over just 2 years. So well number 2 is not going to be a sustainable source of drinking water. Well number 1 will be a sustainable source of water so far. We don't know what the precipitation conditions are in the long term. So which area is recharged by its well? The rural area or the urban area aquifer? Well, which one has more water right now? You can say something about the rural area in the model. In which area was there more evaporation? Well, let's go look back at this model here and look at what evaporation is. These tiny green dots here on the model are evaporation. So let's keep running this model. And I don't see a lot of tiny green dots here. If irrigation is done well, like with drip irrigation, tiny tubes that are laid on the soil and water just drips out, there's very little evaporation. But if you look over here in the city, there's lots of green dots going up because water is pooling and puddling all over the city. So if you look, there's lots of little green dots going up from the city. That represents evaporation. So I'll give you some hints on how to write question 13 and 15. So we know for question 12 and question 13 that more water is in the rural aquifer because we can look at the graph. You should mention the graph in your answer. The rural well seems to have a steady supply of water according to the graph. We see more water in the aquifer here. So over time, this rural well will be probably more sustainable. Urban areas have more water on impermeable surfaces after precipitation. So the water is just sitting on the pavement, sitting in puddles on the street, on the sidewalk, or perhaps like playgrounds. And it's not soaking in. So if the water is just sitting around, it often will just evaporate. In the next video, we'll do page 4 and talk about how water supplies are often transferred from one aquifer to another. See you next time.